Welcome to this explainer. Today, we're looking at the microscopic building blocks of, well, our entire universe. Look, if you've ever stopped to wonder how a solid piece of wood, a glass of water, and the invisible air we're breathing right now are all fundamentally connected, you are absolutely in the right place. Chemistry isn't just a bunch of boring equations in a textbook. It is literally the instruction manual for reality. Every single texture you feel and every breath you take is driven by the rules we're about to uncover. We're going to break down the sheer brilliance of chemistry today, starting way down with unseen particles and zooming all the way out to macroscopic, real-world reactions. So, let's get started.
So, here's our roadmap for today. First, the building blocks of matter. Second, navigating the periodic table. Third, elements, molecules, and compounds. Fourth, physical versus chemical changes. Fifth, the conservation of mass. And finally, how to separate mixtures.
Okay, let's dive into this with a really common, everyday mystery. Where exactly does the wax go when a candle burns? Think about it. You light a thick, heavy candle on your table. You sit by it, let it burn for a few hours, maybe read a book. And when you look back, the candle is half its original size. Almost all of that dense, heavy wax is just gone. It kind of seems like it magically vanished into thin air, right? Well, hold on to that thought. We are going to solve this exact mystery by the end of this explainer using the fundamental laws of the universe. Section 1. The building blocks of matter. Understanding solids, liquids, and gases. Now, to solve macroscopic mysteries like our candle, we have to start small, very small. By definition, matter is absolutely anything that takes up space and has mass. Everything you can touch, everything you can see, even the invisible air filling the room you're sitting in, it's all matter. Imagine zooming in on a single grain of sand, way past the microscopic crystals, down until you see these incredibly tiny, buzzing, restless particles called atoms and molecules. They literally make up everything.
Now, the three main states of matter on Earth are totally dictated by kinetic energy, basically how energetic and how spaced out these tiny particles. Think about water. When it's frozen as solid ice, those particles have super strong attractive forces. They're packed incredibly tight, just sort of vibrating in place in fixed positions. That's what gives a solid a definite shape and a definite volume. But if we add some heat, we're adding kinetic energy. The ice melts into liquid water. The particles still have a definite volume, but now they have enough energy to break those rigid holds and slide past one another fluidly, basically adopting the shape of whatever cup or container you pour them into. Now give them even more energy by boiling that water. They become a gas, steam. With massive kinetic energy and practically no mutual attraction left, these gas particles bounce around freely and violently, expanding to completely fill whatever space they're given.
Moving to Section 2. Navigating the periodic table. The chemist's ultimate cheat sheet. So, now that we know how these basic particles behave under different energy conditions, let's look at the different flavors of matter. We categorize these pure substances as elements, and to keep track of them all, we rely on the periodic table. Back in 1869, a brilliantly intuitive Russian chemist named Dmitry Mendeleev organized all the known elements based on their specific properties. And his arrangement was so incredibly genius that he actually recognized repeating mathematical patterns in nature. Get this, he even deliberately left blank gaps in his table for elements that hadn't even been discovered yet. He just knew they had to exist, and he predicted what they would look and act like with stunning accuracy. Now, while Mendeleev originally used atomic mass to build his table, our modern version is perfectly organized by a much more precise metric, the atomic number. This is the exact number of positively charged protons sitting right in the center, the nucleus of an atom. You read the table from left to right, top to bottom, and this single number uniquely defines an element's chemical identity. It's basically the ultimate ID badge. If you have an atom with one proton, it is always hydrogen, always. If you somehow force another proton in there, it fundamentally transforms into a completely different element, helium, which has two. Add another, it's lithium with 3. It's nature's perfect, unbroken sequence for building the universe.
Now, what's really interesting about this slide is how we can easily carve up this entire table into 3 distinct territories to better understand how things interact. The vast majority of the periodic table, like the entire left 3/4, are metals. Think of copper wiring or heavy iron beams. They're shiny, they're malleable, meaning you can hammer or bend them, and they let heat and electricity flow right through them effortlessly. Then tucked way up in the upper right corner are the nonmetals, like sulfur or oxygen. These are essentially the exact opposites of metals. They're dull, they're extremely brittle if they happen to be solid, and they are just terrible conductors. But right in the middle, dividing those two giant groups, is this diagonal zigzag line of metalloids. These are our rule breakers. They have intermediate properties. They act as semiconductors, meaning they can conduct electricity, but only under specific, highly controlled conditions. And because of that one unique trait, metalloids like silicon form the absolute beating heart of every modern computer, microchip, and smartphone we use today.
All right, section 3, elements, molecules, and compounds, putting the pieces together. So we have our elemental building blocks neatly organized. But reality isn't just single, isolated atoms floating around by themselves. What happens when these restless little atoms start holding hands and combining? Well, this is where the terminology often trips people up, mixing up molecules and compounds. But we're going to clear that up once and for all right now.
To visualize the difference vividly, I love this analogy. Imagine an atom is a single leaf resting in your front yard, just one distinct piece. When a few leaves blow together and get stuck into a specific clump, that clump represents a molecule. Now, if you look closer at that clump and realize it's made of entirely different types of leaves, say an oak leaf, a maple leaf, and a birch leaf all stuck together, then that specific diverse clump represents a compound.
So, the crucial point is all compounds are molecules, but not all molecules are compounds. Make sense? A molecule is simply any two or more atoms chemically bonded together. It can even be the exact same element partnering up. For example, two oxygen atoms happily pair up to make the breathable O2 gas in our atmosphere. That's a molecule, but it's not a compound because there's no variety there. A compound, on the other hand, absolutely demands diversity. It requires atoms of two or more different elements chemically combined in a fixed, unchangeable ratio. So two hydrogen atoms and one oxygen atom bonding together form H2O, pure water. Because it contains different elements, water is a compound.
Section 4. Physical versus chemical changes. Changing form versus changing identity. Now that we've successfully built our complex compounds, let's watch them interact in the real world. Matter is constantly changing all around us, but not all changes are created equal. First, we have physical changes. This is like melting a block of ice into liquid water or taking a piece of paper and ripping it into confetti. The outward appearance changes drastically, sure. The physical state might shift, but the underlying chemical formula remains perfectly unchanged. Melted ice is still H2O, and torn paper is still just paper.
But a chemical change? Now that is a total identity shift. During a chemical change, chemical bonds are actively breaking apart and forming new connections to create entirely new substances. And because we obviously can't see tiny individual atoms rearranging with our naked eye, we rely on macroscopic clues to tell us a reaction is actually happening. If you mix things together and suddenly there's a huge temperature shift, like heat radiating from a roaring fire, that's a chemical change. If a bright flame appears, or if your dark iron nail suddenly transforms over time into powdery orange rust, bonds are breaking. Or, my personal favorite, if you mix two clear liquids and a solid yellow powder instantly materializes out of absolutely nowhere, a really cool process called precipitation, you have just witnessed a chemical reaction. The original substances are completely gone, replaced by something chemically brand new.
Section 5. The conservation of mass. What goes in must come out. Which brings us to one of the most profound and fundamental rules of our universe. Back in the late 1700s, a brilliant French chemist named Antoine Lavoisier ran a series of truly meticulous experiments. He placed reactions inside closed, perfectly sealed glass containers, and he discovered something incredible. Even though matter can undergo these massive chemical identity changes, like a solid piece of wood violently burning down into a tiny pile of ash, matter cannot magically appear from nowhere, and it cannot disappear into nothingness. This became known as the law of conservation of mass. And this brilliantly illustrates the absolute logic of the math behind a balanced chemical equation. Imagine a perfectly sealed closed container sitting on a highly sensitive scale. If you chemically react 300 grams of substance A with exactly 100 grams of substance B, the reaction might spark, it might bubble, it might change color violently. But when it's all done, you will always get exactly 400 grams of your brand new compound AB. The total mass of your starting ingredients, the reactants, must perfectly equal the mass of the final products. The atoms merely rearranged their partnerships. Not a single solitary atom was lost in the process, and not a single one was created.
So, let's call all the way back to our hook question from the very beginning. Where did the wax go when the candle burned? Well, the wax didn't vanish into nothingness. The solid wax underwent a chemical change, reacting vigorously with the oxygen in the surrounding air. As the flame burned, the wax chemically transformed into invisible gases, specifically water vapor and carbon dioxide. If we could somehow trap that burning candle inside a completely sealed glass box and weigh it before and after it burned out, the mass on the scale wouldn't change by a single microgram. That heavy wax and the oxygen simply transformed into an equal mass of invisible floating gases filling the box. Mystery completely solved.
Okay, final section. Section 6. How to separate mixtures, pulling the pieces apart. Let's scale all the way back out from pure chemical compounds to mixtures. Most of the matter we interact with on a daily basis, like a tossed salad, a handful of dirt, or a cup of ocean salt water, are mixtures. They are physically combined, but they are not chemically bonded together. And because they're just physically sharing the same space, they retain their individual properties. So we can exploit those unique physical properties to pull them back apart.
Let's move to and see how this builds a really practical toolkit for literally any chemist or engineer out there. If you want to separate a mixture, you just use their physical differences against them. Step 1 is filtration. If you have a solid mixed in a liquid, like muddy water, you just pour it through a porous filter. The water easily passes through, while the larger dirt particles get trapped. Simple. Step 2 is evaporation or distillation. Got salt totally dissolved in water, just apply heat. The water's boiling point is much lower than the salt's, so the water turns to vapor and escapes, leaving the solid salt crystals behind, which, by the way, is exactly how we can purify drinking water on a massive scale. And step 3 is magnetic separation. If you have iron filings mixed with a pile of sulfur powder, just wave a strong magnet over it. The iron jumps right out of the pile to the magnet, leaving the non-magnetic sulfur safely behind. It's incredibly satisfying to watch, and it relies entirely on physical properties with absolutely zero chemical reactions required.
Wow! We've covered an incredible amount of ground today, from the energetic wiggle of solid particles to the meticulous organization of the periodic table, right up through identifying chemical changes and physically separating real-world mixtures. But I want to leave you with this final, kind of mind-blowing thought. Think back to the law of conservation of mass. Matter is never, ever created or destroyed in any of these processes. It simply changes form. That means every single atom in your body right now, every atom of carbon in your skin, oxygen in your lungs, iron in your blood, wasn't magically created the day you were born. It's been around since the dawn of the universe, forged in the superheated hearts of ancient collapsing stars. And right now, it is currently